Hello, this is Gene Fry. I started studying global warming 30 years ago when I got my PhD from Cornell in resource economics. A few words about me. I spent most of my career working on evaluating savings from energy efficiency programs, 13 years at the Massachusetts Utility Commission, where that was half of what I did. I also had a project there in 1991 to figure out the damage cost from various pollutants, especially greenhouse gases, CO2, methane, etc. I had a short stint at the energy office in Maine before that, and a while afterward, I worked for 3 years on much the same subject in for Western Mass Electric Company and Northeast Utilities. I've also worked for several years for environmental newsletters where I wrote up probably a couple hundred of summary articles about climate change, and very briefly for a consulting company evaluating savings estimates. I've talked about 60 audiences on climate change, handed out CDs with a library of articles on the subject to 25,000 people over an eighth of a century. And I've spoken not only to 60 audiences, but four of those actually were keynote addresses to conferences on 3 continents. So let me share with you today what I've spent much of my lifetime learning, uh, why we need to make climate change a much bigger priority. So let me put this, make this smaller. Stay with you a little bit here and move this down here. There. Okay, feedbacks. Why carbon neutral is no way not good enough. So table of contents, introduction, 12 slides. Climate history, also 12. Climate change drivers, the feedbacks, 15. Putting the feedbacks together, 6. Climate futures, 11. And our solutions, 16 slides. So here are the mechanics of global warming, a nice diagram I found. We burn fossil fuels, put more carbon in the air, which causes temperature to rise. That thaws permafrost, you get more greenhouse gases, CO2 and methane. And when you raise temperatures, ice and snow melt. Melting ice and snow reflects less sunlight, which warms things up. Rising sea temperatures does its share of melting and also raises sea levels. You get more acid ocean, change ocean currents, and have more severe weather here. Some of those are called tipping points. Key misconception, which I'm dedicated to trying to write: when we stop putting carbon in the air, Earth's temperatures stop rising. Instead, it only stops rising when the feedbacks, mostly reflection or albedo and water vapor, have played out. Earth has had this much CO2 in the air before, millions of years ago, most recently. It was much hotter then. This study examines the factors that threaten to make it that hot again. Word about how I got started in 1989. I saw the maps on this slide. Another part of the study, I found the next year, food production fall 30 to 50% modeled by 2059 as temperature rose above 4 degrees Celsius relative to 1880. That captured my total attention and has held it ever since. So these are the maps, supply-demand drought index, which is basically soil moisture. Once a century drought at the bottom left is in dark brown, once a decade drought in red and orange, once a century flooding in dark green over at the right of that scale. And this is the business as usual emissions scenario. Continued growth in CO2 emissions burning fossil fuels. Here's the baseline. They look 20 years in their past, which is now 50 years in our past. The white areas cover a significant fraction, and you get the yellow areas, and the lighter green areas are roughly similar. And we see one once a century drought patch covering somewhat around 1% of Earth in Southeast China. 30 years later, 10 years in their future, 20 years in our past, you see once a decade drought stretching from Venezuela to Korea. There are some wet spots mostly in the Arctic and also in Central North America, and a few spots around the ocean. Okay, looking 30 years farther in the future, which is 40 years in their future, 10 years in our future, you see once a decade drought stretching from almost from Hawaii to east of the Philippines and covering a large chunk of Earth's surface. Once a century drought in northern India into Tibet, also in East Africa and in the Western Sahara, and a little bit maybe around Mexico. Okay, 30 years farther in the future, which would be 70 years, I think, in theirs and 40 years in ours. Doubled CO2, and at this point we have 4.2 degrees Celsius warmer, I would say. Temperatures would rise after that, even if we cut off CO2 emissions. Take a look at once a century drought spreading to cover almost half of Earth's land surface. Intense rainfall and flooding in the Arctic, especially the Arctic Ocean, is starting to be the case in Antarctica. Lead author is the one who presented this that I saw, David Rind. His boss was James Hansen. Cynthia Rosenzweig, the agriculture expert, was also in on that study. Well, here's our situation. We have run off a cliff and we're just starting to realize it. I call it overshoot with lag effects. The splat comes later. What we need to do is get a parachute and claw our way back to the cliff. Feedbacks, mostly albedo, mean it's going to get much hotter. So the greenhouse effect you're acquainted with, visible light, shortwave, strikes the Earth, gets absorbed, heats up Earth, outgoing long-wave radiation. Some of it gets intercepted by greenhouse gases and radiated back down. The darker the Earth is, the more it absorbs, and the warmer it gets. The more greenhouse gases, also, the warmer Earth gets. So there are two major effects. Here's the other one, the albedo effect. Sunlight strikes a light-colored surface like snow and ice, and most of it gets reflected. Change that to water when the ice and snow melt, and almost all of it gets absorbed. Light surfaces don't warm Earth much. Changing a light surface to a dark one warms Earth. Changing a dark surface forest to a lighter one, like grass or desert, cools Earth. So the principal albedo effects, that especially the ones I will be examining, come from clouds, sulfates from burning coal, sea ice, snow, and land ice. There are two types I'm not dealing with. Soot, also known as black carbon, don't really know the sign in the future. More forest fires, but less diesel, maybe less cooking smoke. Vegetation changes, although there will be some forest growth darkening the Arctic area. Elsewhere, we'll be changing forests to savanna and grasslands, which will be lightening, which will have a cooling effect. On balance, more likely than not, will be a modest cooling effect. The principal greenhouse gases warm Earth's surface from 0 degrees Fahrenheit up to about 60. The most important of those is water vapor. As Earth warms up, evaporation increases water in the air. This amplifies warming from other greenhouses, but also from higher albedo warming. Carbon dioxide is the next most important greenhouse gas. It does 52% of the rest. Comes from burning fossil fuels. Coal emits about twice as much as natural gas. Methane, CH4, natural gas, does 30% of the rest, some of it indirectly. The human sources outweigh the natural sources almost 2 to 1. And the other greenhouse gases, refrigerants, nitrous oxide, mostly from agriculture, and various other gases. My words about global climate models, they've improved a lot. Earlier ones often omitted large-scale changes in permafrost, sulfates, and clouds, giving a systematic bias because they did not understand them well enough. They often also underestimated how fast Arctic sea ice would melt, and climate sensitivity. I'll say more about that after a bit. They also stopped in 2100, giving the mistaken impression that climate change stopped them. As things that were left out got put in, scientists said repeatedly over the years, it's worse than we thought. And you can see that from one IPCC report to the next, also with the National Climate Assessments. So climate history. Going back to the time of the dinosaurs, we had a much warmer period in red, and then you started to be cold enough so that ice would form in Antarctica. And much more recently, just a few million years ago, in the north, especially Canada and Alaska. Siberia some too. Temperature can rise suddenly. 55 million years ago is perhaps the best analog of what's happening today. Over at the right, when you have enough ice, there's big swings between ice covering most of Canada and a third of the United States, and covering almost none of Canada and none of the United States, except for a few isolated glaciers in Glacier Park, which are vanishing. So we're in a period where, geologically speaking, temperature changes are happening fast, and there are big changes in ice sheets and CO2 concentrations. Since the thermometer era began in 1880, where NASA's thermometer set, temperatures have risen 1.25% since a century ago. The past 12 months have been the warmest on record. The rate of change is accelerating. It's twice as fast in the last 20 years as it is in the last 100. The land surface is on target to breach the 2 degrees Celsius target in 2035 at present rates. So the Keeling curve, many of you have seen the sawtooth version, depending on whether the northern hemisphere trees are leafing out or shedding their leaves. But these are annual averages. CO2 is up 47% since the start of Industrial Revolution, 40% since the thermometer record started. Methane levels up more steeply, especially in the 19th century. And there's the maximum between the last several ice ages. And we've blown way past that, as you know. Earth's 100-year surface warming rate is 7 to 30 times the previous record in the history that I could find. The last time CO2 hit 400 parts per million, 4 and 14 million years ago, Earth's surface averaged about 7 and 10 degrees Fahrenheit warmer than now. Seas were 65 to 135 feet higher. Kansas was hot as Las Vegas now, and Florida was mostly underwater. This past is our guide to our future unless we get our act together. In more detail, today's CO2 level is the highest since 14.1 to 14.5 million years ago, when CO2 was 430 to 465 parts per million. Deep ocean temperatures range from 4.6 to 6.6 degrees Celsius warmer over those 400,000 years. Seas were 25 to 40 meters higher, restating the feet. CO2 levels were almost as high, 357 to 405, 4 to 4.2 million years ago, that's 200,000 years. Sea surfaces are about 4 degrees Celsius warmer, and seas were almost as high as they were 14 million years ago. Sea levels mean ice then was gone from almost all of Greenland, most of West Antarctica, and some in the east. As you may know, 2/3 of the ice in the west is grounded below sea level, but so is 2/5 in the east, and the east is much bigger, so there's twice as much area grounded below sea level in the east. Sediments show that ice in those days retreated hundreds of kilometers inland, so there's precedent for great ice sheets melting. Now, Vostok is just a few hundred miles from the South Pole, and is the coldest spot on Earth. Long record for hundreds of thousands of years. This particular one is 425,000 years. Temperatures now are near the top end of that range. The CO2 levels and the methane levels are off the charts. That's a rough approximation. Okay, talking about the next two slides. The next one, we're going to get rid of the temperature axis along the bottom and plot temperature, which is the red lines, against CO2, which is the blue lines at the top. And we're going to do that as blue dots, and then show the trend lines, the best fit, first with CO2 only, and then with CO2 and methane, CH4. On the slide after, there'll be a bunch of commentary. And there are the sources for the data from 4 and 14 million years ago. So lessons for our future from ages ago. This is looking at 420,000 years, blue dot every 10 years, CO2 in the atmosphere versus the temperature at Vostok. Now, global temperatures go up more slowly than those at Vostok. And a good study in 2016 from Carolyn Snyder is what I used to convert the temperature range at Vostok to the estimated temperature range globally. The purple line is for CO2 only, and not shown. There's also information on CH4 as methane. That's the green line. So here are the two equations for those two trend lines. The first uses CO2 only. That's in purple. It explains some 73%. That's a correlation of about 0.86. Also using the information on methane gives a better fit. It explains more of the variation. And gives you the green line. There's the information from 4 and 14 million years ago. To my surprise, these are both on the same line, derived from times colder than now. These other times are warmer than now. CO2 levels today, 410 to 415, depending on which month, and methane levels around 1860. So climate sensitivity, I said I'd tell you about this. These are long-run climate sensitivity because you have a lot of time to adjust. We're looking now at short-run climate sensitivity in the general scientific community. The equation, the purple line, is long-run climate sensitivity at Vostok. You translate that by using 0.6 to get the global climate sensitivity long run at 8 degrees Celsius for doubled CO2. Those are the estimates from the data that I have. The rule of thumb has been 3 degrees Celsius is the best estimate of climate sensitivity. Anyway, today's estimated equilibrium temperature from today's greenhouse gases relative to 1880. Plugging in 412 to the purple equation gives you 4.8 degrees Celsius from today's CO2 level. You add methane over at the right, 1860 times 7.504, and you get 8 degrees Celsius warming from today's greenhouse gas levels. That's a lot more than we've seen so far, which is, depending on how you measure it, 1.1, 1.25, or 1.8. Again, global surface temperature using that same equation. We're going to see what does it take to keep warming to 2 degrees above 1880. For example, using pre-industrial level of methane, 694, requires 317 parts per million of CO2. This in turn requires removing 70 to 75% of the CO2 we have already emitted, all our future emissions, and all our methane emissions past and future. Humanity's remaining carbon budget to hold warming to 2 degrees Celsius for burning fossil fuels is negative 310 billion tons or gigatons. That's a lot less than the positive 450 or so, even 500 that many analysts have posited using a rule of thumb connecting cumulative CO2 emissions to temperatures. I think they've neglected albedo effects, and anyway, only a tiny fraction of atmosphere warming goes into the atmosphere. That's the purple stuff, almost next to zero. It's sometimes hard to see. That's what we measure. That's what people are concerned about when they call global warming. Actually, almost all the heat goes into the ocean, upper and the deep ocean. 2 to 3% goes to melting ice, some 2% to heating up the land surface, the soil, and so forth. We are the tail in that purple area wagging the dog, which is the whole thing. Looking more closely now at the ocean, one of those marks on the left is 100 years of US energy use, census scale. The rate of warming has increased. The first period up to about 1990 was 0.4 times one of those marks, 40 years of US energy use every year, then 70 years of US energy use every year, and now we're about 100 years of US energy use, or 17 times all human energy use. By now, the oceans gain about as much heat every 3 years as all the energy humans have used cumulatively. That's huge. So climate change drivers are going to look now at several feedbacks. First, the concept of tipping points. There are various versions of this. I first came across this in 2006. What would make climate change accelerate so natural forces defeat our efforts to slow it? Disappearance of sea ice, that was in the original diagram. Carbon sinks fade in oceans and forests. Some become carbon sources. We're seeing that in the Amazon. We've also seen that not so much in temperate soils yet, but that's in our future. And methane released from permafrost. More about that later. Permafrost also releases CO2. Depends on CO2 where it's dry and methane where it's wet. Water vapor. 1 degree Celsius warmer air contains 7% more water vapor, which increases radiative forcing by 1.5 watts per square meter. That's a lot. 86% as much as from CO2 we've emitted, and 45% as much as all our other greenhouse gases emissions, except for water vapor, of course. The albedo effects, again, we're examining clouds, sulfates, sea ice, snow, and land ice. Starting out with clouds, only half the sunlight reaching our atmosphere makes it to the surface. The barriers, clouds, sulfates, which we'll also examine, blue sky, backscattering, and the ozone layer, which we're not paying attention to here. So, 3 slides about clouds. Orientation, they reflect some sunlight away, cooling Earth, but they also keep outbound heat in, warming Earth, especially at night. Many factors affect them. At night and going up over mountains, air cools. Cool air holds less water, the opposite of warmer air holding more water, so it'll often cloud up and rain. Clouds cover a little over half of Earth. On balance, the cooling effect outweighs the warming effect. Low clouds cool Earth more than they warm it. High clouds, cirrus clouds, do the reverse. Changes in cloud area, altitude, and opacity affect global temperatures. We'll look first in words, and the next we'll see a graph. Cloud cover area is shrinking a little for a warming trend. More high clouds and fewer low ones also yield a warming trend. Low clouds are growing more opaque for a cooling trend. Net result is a warming trend, 10% of the total. So here's the best diagram that I've seen. Understanding clouds is very difficult, and the effects in aggregate are subtle. We're not sure that clouds actually have a warming effect, but it's fairly likely that they do, and if so, it's big. So Zelenka estimated that 1 degree Celsius warming would add 0.47 watts per square meter per degree C for the next 16% to warming otherwise. The error bars for the cloud effect, according to IPCC, extend from negative 0.2 to positive 1.4. So it's pretty likely, but not certain, that clouds have a warming effect. I'm going to use Zelenka's 0.47 rather than the midpoint from the IPCC, which is a bit larger cloud effect. Switching now to sulfates, a couple with words, and then the graph. Dark sulfates in the air block sunlight, cooling Earth. They make haze, cloud condensation nuclei. More sulfates, cooler. Most sulfates come from burning coal, some volcanoes, some dimethyl sulfide from phytoplankton on the crest of ocean waves. A little chemistry up in the air. Sulfates fall out after a few days. We have to keep pumping more to keep the sulfate levels up. Sulfates have actually fallen by almost a quarter from 1979 to about 2002 or so. They used to offset 40% of warming. Now it's about 30%. As we stop sending up SO2, warming will catch up. Okay, here's the graph. Sorry, there are just 2 here on sulfates. And I have a long equation at the very end. Sorry to hit you with that, but it's important to know that some of these are based on real science. So volcanic eruptions are important. See, the temperatures fell dramatically with Krakatoa, 2 in the Caribbean and 1 in Guatemala. Cut temperatures around 1905, Katmai and Kamchatka around 1915, Agung. But the big thing is how human sulfur emissions rose 110%, and that's why temperatures leveled off from 1940 to 1975. Human sulfur emissions, as I mentioned, are down 23% from their peak, but they're still 3 times the levels in 1880. So there's the equation. It includes CO2, methane, and sulfates. The adjusted R-square is very high, correlation more than 99% between the predicted and the actual. And all 3 variables are highly significant. So on the land has been warming faster until the last 15 or 20 years than the sea surface. And although combined is 1.25 in the last century, we have 1.8 for the last century and a third on the land surface alone. Okay, third topic, sea ice. And particularly we look mostly here at Arctic sea ice. The volume has been decreasing faster or farther than the area has. The area is down by almost half. The volume is down more like 3/4. That's because the ice got thinner. As the original diagram showed, as ice recedes, Earth absorbs more heat, its surface will warm more, even without more CO2. A lot of things happen without more CO2 because of the feedbacks, the warming effects. So this is a diagram of the sea ice volume. The minimum, which is seen on the previous one, is in magenta, suggests that we'll see a few ice-free days sometime later this decade. July and November are in orange, and that suggests we can see some ice-free summers next decade or possibly early the following. And then June and April is when the minimum is, and that suggests sea ice will be gone in the Arctic all year before the end of this century. So now the words about sea ice. Hudson did a study back in 2011 that I've used for some years now. It estimated that sea ice loss would warm Earth's surface by 0.7 watts per square meter, of which 0.1 had already occurred. Antarctic sea ice covers a similar area, but the trend is not yet clear. Record highs area in 2013 to 2015, record low 2017 to 19. This year it's below average, but not going to be record low. Okay, next topic, snow. Research by Chen and found that from 1982 through 2013, radiative cooling from northern snow cover decreased by 0.33 watts per square meter per degree Celsius. That's about 2/3 of what the clouds are. This was due to earlier snow melt in the spring and added 12% to greenhouse gas warming. Now, looking at the mean extent of snow, not just the timing of it, is something I did a couple of years ago. How do days of snow cover change as the Earth warms up? Well, of course, they decrease. Just think about Winnipeg with long snow season and New Orleans with none. So I did analysis with 14 US and Canadian cities along the same meridians to correct for how far they were from the ocean. The upshot of that is estimate a 9% decrease in Northern Hemisphere snow per 1 degree Celsius global warming. Somewhat more than that in the study area, but the study area did not go north of Winnipeg, which is where most of the snow is. Okay, next topic, land ice. Greenland and Antarctica split in 2 parts. Greenland's net ice melt rate rose 7 times over the past 17 years. It's a lot of ice melted. Antarctica has lost half as much, but has 9 times as much to start with. Its ice loss rate tripled. What that means in both the south and the north, ice loss has been accelerating 12% a year. I project future land ice loss later for sea level using S-curves. Land ice area decreases far more slowly than sea ice area because it's so thick. So its albedo change effect is much slower, for very little effect so far, and the sea level rise effect is much slower still. But that's not something I examine in any detail here. Putting feedbacks together the past 45 years based on what you've seen, and then projecting those out, introduction to that, out to 2400. So in summary, an estimated 39% of warming over those 42 years came from changes in albedo or reflectivity, including the indirect effects of clouds and water vapor shown in the third column. The most important of those is sulfates loss, 0.185, followed by snow cover timing change, 0.092, and Arctic sea ice loss, 0.051. Total is 0.33 degrees Celsius compared to 0.839 degrees Celsius total surface warming over that period. 0.33 over 0.839 is 39%. Warming in the future to 2100 and especially beyond will be dominated by albedo changes and their feedbacks. That's especially true as we cut our own emissions. So I wondered, what would the picture be like if we distributed these effects to water vapor and clouds, which are kind of immediate feedbacks? Water vapor, 36% of the total warming, CO2, 17, sulfate, fewer sulfates, 12%, cloud change is 11, methane, 10, earlier snow melt, a little less than 6, other greenhouse gases a bit further less than 6, less Arctic sea ice so far, 3%, and less land ice, trivial. These will all, the ice and the snow and the clouds and the water vapor will definitely get to be more prominent in the future. So totals water vapor, 36%. Our greenhouse gas emissions from burning fossil fuels primarily, 32. And albedo changes just as much. That's the past. Okay, now the words about permafrost, about twice as much carbon as we have in the atmosphere, depending on what depth you measure to. Permafrost emissions over those 42 years have not been quantified well, probably small till recently, and now comparable to those from US transportation. So here are 6 graphs depending on climate sensitivity. I think 4.5 is certainly a better estimate than 3, especially if you're talking about long run. These are medium run, actually. And the amount in the soil, amount in the permafrost is in red, falling from 100%. The amount in active soil varies from case to case. The amount in the atmosphere goes up. And the higher temperature scenario is the second line. The lower temperature scenario is the top line. So with faster rising temperatures, almost all the carbon in the permafrost gets into the atmosphere. The result, depending on the scenario, there are uncertainties in all scenarios, range from about 0.2 degrees Celsius warming to about 1.6. And that depends on how sensitive the climate is, how much carbon we emit, and other factors. There are uncertainties all over the place. Anyway, the impacts of these factors will continue. They will be much greater in the future until Earth's ice and snow are gone. By that time, the climate sensitivity will have declined dramatically because you no longer have the ice and snow loss feedbacks. It'll just be greenhouse gases, and climate sensitivity to greenhouse gases themselves is actually less than 3 degrees Celsius per doubled CO2. A good bit less, actually, more like 2. Earth will warm 3 to 4 times more even if we stop emitting now. Parcel that out among sulfur emissions when we stop burning coal, vanishing northern sea ice about the same, receding northern snow cover also, vanishing southern sea ice somewhat later than northern, and permafrost, etc., which also includes other natural sources, methane hydrates, outgassing from soils as they warm up, and ocean as warmer water holds less gas in solution, receding land ice, and warming the oceans enough so energy out equals in. Those latter two will continue long after 2400. The top 5 are probably going to be complete or mostly complete by 2400. Warming the oceans enough from current CO2 levels, at least 0.6 degrees C in total, and maybe as high as 0.9. Land ice, probably comparable. And water vapor and less cloud cover, 1.7 multiplier, 1.68 to be more exact. Is my estimate, but the estimates have error bars, so 1.7 is fine. If carbon emissions don't peak until 2035 instead of ceasing immediately, you get a lot more warming, 2.5, 3.5, 4.7 degrees Celsius more by 2400. That's twice the heating from stopping emissions now. Moreover, unlike cutting emissions cold turkey, warming, which basically stops warming by 2400, warming in this case continues long after 2400. So looking at our climate futures, a mixture of my projected scenarios and the damages estimated back in 2006 for perspective on those. Start out with the damages. 2 degrees Celsius warming, that's the Paris target going back to Rio in 1992. Stern Review, dozens of scientists headed by the World Bank's chief economist. These are what we cannot avoid. We're too late. Hurricane costs doubled, many more major floods. Major heat waves are common. Forest fires worsen. Droughts intensify. Deserts spread. Water wars increase. We've seen them starting in Darfur. We've seen some in the Middle East more recently, from Yemen to Syria, etc. Crop yields rise nowhere, fall in the tropics. Ice cap collapse becomes irreversible in Greenland and West Antarctica, and sea levels begin rising more quickly. So I did 6 scenarios. XFF means fades out fossil fuels by 2050. And CDR is carbon dioxide removal. Cold turkey means we stop our emissions now. XFF has 3 of them that are phase out fossil fuel emissions by 2050. We have peak in 2015, but keep on emitting fossil fuels in past 2100, a higher peak if we peak in 2035. So soil carbon loss since 10,000 BC is 60% of fossil fuel emissions to 2000 is about 40% of what we've emitted by now. CO2 removal in one case is perhaps 2/3 of that, and in another case, it's somewhat more than soil carbon loss. Soil carbon loss includes both less carbon in the soil that remains and the loss of soils that get eroded away to the ocean. So these emission scenarios have implications for atmospheric CO2, but the atmospheric CO2 is actually quite a bit more than you would get just from the human emissions, because they have feedbacks from permafrost and the other carbon reservoirs that I mentioned, soil, ocean, forests, etc. So if we stop emitting fossil fuels by 2050, for instance, our emissions alone would keep concentrations to about 500 parts per million, but when you add in the natural sources, the feedbacks, the tipping points that we've passed to kick those feedbacks in, it's around 720. Similar for other ones. To really get things under control, as you can see, to get them lower than today's level, you have to take carbon dioxide out of the air, and the more we take out, the lower the CO2 levels. And that has implications also for temperatures, which we'll get into in a minute. Okay, 3 degrees. This again from the Stern Review. We can delay these or avoid them with massive CO2 removal, as you'll see in another slide or two. Throughout hurricane, much worse. Water becomes scarce, fresh water in particular. Crop yields fall substantially in many areas. More water wars and failed states. Terrorists multiply. 2/3 of the Amazon rainforest may turn to savanna and desert scrub. We may have passed that tipping point already at around 20% loss, according to Antonio Nobre, Brazil's leading expert on climate change in the Amazon. Tropical diseases spread farther and faster. If you think Lyme disease is bad, you ain't seen nothing. 15 to 50% of species face extinction. The rate is already, for mammals, is a few hundred times the background rate, not that different from other vertebrates. Okay, looking out now, not to 2400 yet, but just to 2100, we see all 6 scenarios give very similar amounts of temperature change, about 3 to 3.25 degrees by 2050, 2060. You can see the bump up when we quit cold turkey and the sulfates fall out, and you get fairly immediate 0.3, 0.4 degree, 0.4 really, 0.36 degrees Celsius warming. But it's better in the out years. Whereas if you keep putting CO2 in the air, and the more rapidly you do with the black line, the worse it gets. And you're seeing some scenarios having temperature increases to more than 4 degrees Celsius above 1880 levels by the end of this century. But it doesn't vary that much depending on what we do because of the feedbacks we've already kicked in. So 4 degrees, which is where we're looking at in most cases at the end of the century, water shortages afflict almost everyone. Crop yields fall in all regions by a third in many. Entire regions cease agriculture altogether, such as Australia. Water wars, refugee migrations, and terrorism become intense. Methane release from permafrost accelerates even more. The Gulf Stream, the Atlantic meridional overturning circulation, part of the global thermohaline circulation, of which the Gulf Stream is part of the Atlantic one, may stop, or at least slow down. It's slowed down 15% since the middle of last century. Monsoons can fail, and land ice collapse speeds up, especially in West Antarctica and also in Greenland. So here's the key slide from the whole show. Temperatures at the global land surface, depending on these 6 scenarios. The worst certainly is the peak in 2035. It's going up toward 10 degrees Celsius, sometime maybe even as early as 2500. Cutting fossil fuel emissions to 0 will get us to 7 degrees by 2400. So the bottom line is the Paris target, 2 degrees. The top one, Kansas gets as hot as Las Vegas is now at about 5 degrees. If current trends continue, 348 cities I've analyzed, including about 9 or 10 in Kansas. Kansas, if warming continues at the rate it's going, will become as hot as Las Vegas around 2100. So we're definitely on track for that. This includes the big albedo effects I've been talking about, the loss of total loss of sulfates and sea ice, loss of a lot of snow, loss of some cloud cover, and some land ice. Land ice loss will continue long after that, and more water vapor in the air. Those last 4 continue after 2400. So here's a picture of what 5 degrees warming might mean. This is my extrapolation. Deserts grow by twice the size of the US. Tundra is replaced by forest in somewhat less than the size of the US as the Arctic greens. World food falls by a third to a half. That's the initial study that I saw 30 years ago. Human population falls a lot to match the reduced food supply. Vegan can cushion that a bit, and reduce birth rates, which we're already experiencing, can cushion that a bit. Other species fare worse. Extinctions are very widespread. Okay, 5 degrees collapses civilization. That's my words. 10 threatens human extinction. That's also my words. So here's my current estimate on sea level rise. I think it's probably a bit on the high side because I've not distinguished between ice that's grounded below sea level and ice that's grounded above, but it's going to be a big problem. There's 2100, which is when many projections stop. There are a few cities that would go underwater at 17 meters of sea level rise. These numbers include thermal expansion of seawater for a few meters, almost total ice loss in West Antarctica, and pretty much also in Greenland. Actually, it'll probably take a bit longer in Greenland than that. And 7 to 35% I've estimated in East Antarctica, depending on our scenario. This may be a little bit high, but certainly the areas grounded below sea level in East Antarctica are vulnerable in that time frame. So using my economist hat, the present value of future damages from global warming is likely to exceed the gross world product. As not many economists will tell you, it could be many times that if we continue business as usual. It's difficult to evaluate extinction of humanity, but it's a lot. So what should we do about this? We should prevent it, of course. So solutions are basically two, and there's a 2A. Stop putting carbon in the air as soon as reasonably possible. Take carbon out of the air, 3/4 of what we've added so far, plus any future emissions. The sooner, the better. And for 2A, solar radiation management, things like sulfates and calcites in the stratosphere, brightening marine clouds, refreezing the Arctic Ocean, mirrors in space, that kind of thing. So the solutions, in a little bit more detail, table of contents: personal, policy, carbon-free technologies, and CO2 removal. So what my wife and I have done, we have a heat pump now, air source, pretty much got rid of the furnace. Electric car, about 85% of our miles. 100% green electricity is actually 140, since we have community solar on top of our wind and hydro. CO2 removal, we'll say more about that at the end. $46 to move 2 tons of CO2 into soil from Blue Indigo. $32 to Climeworks to turn CO2 into stone. We've decreased our carbon footprint 80%. There's still some for water heating, for our backup car, for some air travel, and for all kinds of the general stuff that we buy. So policy solution, absolutely. Tax carbon across fossil fuels worldwide in proportion to carbon content. Impose a tax upstream. It should start low, but then rise briskly on a preset path. They need to be return net proceeds as equal dividends to individuals and subsidies for fossil fuels. This is a month before the Paris Climate Agreement. All the world's leading economists reiterated essentially 3¼ years later by America's 45 leading economists, all our Nobel Prize winners except for one, all surviving ex-Fed chairman, Council of Economic Advisors, etc. It's really important that we have a preset path so people can plan and plug into their spreadsheets about what investments they're going to make, what equipment they're going to replace when. If they know the carbon price, they'll be able to make reasonable decisions. And they will, you'll be amazed at the progress that's made with the carbon price on carbon. Citizen Climate Lobby, we now have 170,000 volunteers. I'm a chapter leader. Proposes $15 per ton of CO2 to start, rising $10 per ton per year. CCL's proposal first went to Congress in 2018. It's reintroduced in this Congress and now has 80 co-sponsors. It includes a border tariff adjustment for the difference between our carbon price and the prices in other nations. Europe's price is now substantial, but a bit lower than where our proposed carbon price will be in 4 or 5 years. Economic analysis shows that CCL's carbon fee and dividend path creates jobs and grows the economy. The effects are not huge, but they're there. 70% of Americans receive more in dividends than they pay in higher costs for higher energy prices. It's an especially good idea for low-income Americans, most of whom use much less energy and carbon. Emissions fall quite a lot, and lives are saved with less air pollution. So I would add to that, pay for verified CO2 removal at the same price that CO2 emissions are charged. Looking now at technologies, the levelized cost of new electric energy, which used to be our #1 source of carbon, it's been cut enough, so now it's #2 behind transportation. Outfit called Lazard has been doing these every year. As you can see, solar and wind are now the cheapest US electricity sources, cheaper than new gas-fired power plants in most places, and also cheaper than the variable or operating costs of coal-fired plants. So the share of generation for solar and wind is rising, and renewable energy more generally. See the next two slides. Here we have renewables generally. It's doubled in the last 10 years. Natural gas has also doubled in the last 10 years, and the bottom has fallen out of the coal market, especially under the Trump administration. Nuclear has been pretty constant. Renewables passed coal in 2020, really, about the same, almost passed them in 2019, passed them in 2020, and are likely to pass nuclear in 2021 or 2022. Now, on some detail on oil and the major renewable sources, the ones renewables not listed here, geothermal and waste primarily, are about two-thirds as much as wood. You see wind rising quite substantially from 2003 and solar quite substantially from 2013. Those are the cheapest. Hydro is already being maxed out at available sites. And this has resulted in, this has been part of the reason that our CO2 emissions have fallen almost 15% since their peak in 2007 under the Bush administration. Now, on the transportation side, battery prices for electric vehicles have fallen steeply, and those vehicle prices will continue falling as battery prices fall. They're likely to follow below petroleum-powered ones over the next 3 years. Their variable costs are already significantly lower. New electric vehicles will crowd out new petroleum ones. You won't see people buying petroleum-powered ones after 2030. As a result, oil use will fall, likely 30% by 2030, and oil company revenues will plummet. This is the current round of bankruptcies is not going to be the only one. What about the other uses for transportation? Well, we have industrial processes, space heating, water heating, ships and airplanes, the other transportation. And you can also convert trains to electricity. That's easy. Why? That's why we price CO2. Innovators will figure out ways to cut emissions in all kinds of sectors we don't otherwise target. Over 10 to 30 years, CO2 emissions can be eliminated for the first three: industry, space, and water heating, using electricity. Deep cuts in the latter two can come from things we know about: wind, nuclear, biofuels for both, efficiency for both, and fast trains, replacing medium-haul airplanes. And other things can happen that I don't even put a name on once you price CO2. So about taking carbon out of the air, 3 slides, pretty densely packed. First one about biology. Farming can put 4.3 gigatons of CO2 per year into remaining soils for $20 to $100 per ton. We're paying $23 per ton to Blue Indigo right now. Organic farms are the gold standard. They can add 1 ton of carbon per acre per year to soils. No-till and compost cover the key practices. These allow fungal networks that supply plant roots to rebuild and flourish. Roots and fungal networks both are key carbon stores. Good practice can restore soil carbon, the soil that's left, to levels before farming. But we only have 20 to 40 years until soil carbon respiration exceeds additions from new roots. So restoring farm soil carbon should yield 8 to 25% of the CO2 removal required. Biochar is wonderful stuff. How much we can do is probably less than changing tilling and compost practices. Maybe 4%, maybe 2%. Biochar is wonderful stuff for drought resistance because it holds water and it stays there for millions of years. Trees are wonderful, but soils will have less water. You're seeing forest fires run wild already in places like California, Colorado, Washington, British Columbia, the Great Smoky Mountains, but especially in Siberia and also in central Canada. Think about the evacuation of Fort McMurray, the oil sands capital in uh, British Columbia, I think it was, or maybe Alberta, about 4 years ago. Problem is when the forest fires run wild, often the forests don't grow back because the climate has changed, the soils and the seeds have burned. So I'm skeptical that afforestation and reforestation will be a major player. Now, the most speculative is farming the oceans. My friend from undergrad back in the 60s proposed growing algae in pans, add fertilizers, harvest the algae, turn them into biochar. Other people have done experiments adding iron filings to the open ocean. That works in a few places. Mangroves are great. They store a lot of carbon per area, but there's only so much shore for them. Kelp and seagrasses. Rebuild rangeland with perennial grasses. Holistic management, add soil carbon faster with short rotation cattle grazing. Deep roots and dung beetles move carbon into the soil. It's really important to cut down methane burps, otherwise you don't get ahead of the game. There's a red seaweed that does that, actually 2 or 3 in that same family. Some question for both of these, how much, if any, net CO2 can be removed. Now for the non-biological ways. Direct air capture blows air through catalysts in artificial leaves or ceramics. $1,100 per ton is what I paid Climeworks, but $500 to $1,000 is better for current. 20 to 138 per ton later at scale. All of these increase the surface area for chemical reactions. You can store it underground or add it to concrete. Storing it underground in basalt is especially good because it turns into carbonate rock very quickly. But it requires more energy to remove CO2 using current methods than burning carbon in the first place yielded. So we need to wait for carbon-free electricity to power direct air capture. Speed up rock weathering by, again, grinding up basalt, etc. So olivine dust, increase the surface area, increase the chemical reactions to take CO2 out of the air. Or spread it on the ocean surface. Lime or small olivine gravel, which decreases ocean acidity. Another phase of taking carbon out of the air and taking carbon out of the ocean, out of the active ocean, put it on the ocean floor. Add small olivine gravel to farming soils. It's a perfect complement to biochar. And then in summary, humans must go carbon negative big time by 2050. So you can direct questions to me. There's my email address, which is also on my website. The website has 19 pages, something close to 100 illustrations, and 500, 600 articles per web page. So the task before us is we need to do what we can to cut carbon emissions. We've known that for quite some time, but we also need to do what we can to take carbon out of the air. Most of the carbon we need to worry about is what is already there. We're making good progress toward cutting emissions, and that's going to be happening rapidly over the next 10 to 25 years. Taking carbon out of the air will need to become the largest industry on Earth. You need to do what you can. Make sure you pressure our leaders and you vote to put a price on carbon for putting carbon in the air. As the follow-up to that, put a price on carbon for taking carbon out of the air. I suggest we use the same price. That price needs to be known and definite. So cap and trade works poorly at that, and regulations, program targets work even worse. But a revenue neutral carbon tax, also known as carbon fee and dividend, is what we need. So thank you for your attention. and best wishes to all of you.